This program is brought to you by Stanford University. Please visit us at stanford.edu.
Today, we're going to have our first encounter with what is called gauge theory. All of modern physics is based, all of modern particle physics in particular, and modern general relativity, gravity physics, all fundamental views of physics, and a great deal, I might add, in condensed matter physics. Not that I don't think that condensed matter physics is fundamental. I should not have made that distinction. But condensed matter physics, particle physics, general relativity. One of the most basic principles is the principle of gauge invariance. I'm sure you've all heard of it. You probably wonder what it is. Some of you may know what it is. We're going to begin with our study of gauge symmetry or gauge invariance, or gauge principle, by studying a simple example. Now, in 1905, Einstein pointed to the importance of very carefully defining and setting up the idea of coordinate systems. That there may be some hidden assumptions that one makes when one speaks of things like, well, simultaneity is of course one of them, but other such things, the length of objects and so forth, and that you really do have to be very careful to operationally and carefully define what you mean by various kinds of concepts, such as simultaneity, for example. So everybody thinks that they know what simultaneity means, but comparing times at different places is not so obvious. How you compare, how you say when two times are equal when they correspond to different places, especially since it takes light time to go from one place to another. So he was very careful, and in being careful, he invented the special theory of relativity. But that, how shall I say, that idea of being careful about defining relative things at different places of space and the ambiguities that could inherently be there because you're trying to compare things at different locations, that theme has sort of permeated physics since Einstein's time. The general theory of relativity makes it even worse, that not only can't you compare detailed simultaneity, but you can't even compare, for example, in an obvious way, what you might mean by my finger is pointing that way over here. You point your finger in some direction. Go ahead, point your finger in some direction. Good. Are we pointing our fingers in the same direction or not? How do we tell? Well, we're looking, and in looking we transfer photons back and forth and so forth. And so we make comparisons by sending photons back and forth. But how do we decide without, without an experiment to send something back and forth, how do we decide whether this and this are really pointing in the same direction or not? Right? Well, one way is to try to carefully bring this over to here and see if they're pointing in the same direction when we line them up. But how do I know that in the process of going from here to here, I didn't rotate my finger? And of course, in the back of our imagination, we imagine that there is located at each point of space an idealized coordinate reference frame that are oriented parallel to each other when we move from one place to another. But maybe that's a idea that is a little too naive. Maybe we have to be more careful in comparing things. Now, we compare all kinds of things, but the specific thing I want to talk about is comparing the phase of complex wave fields. A very, very important example of comparisons at different points has to do with complex wave fields. Now, remember, complex fields, we've discussed them. I called a field phi when it happened to be made out of two real components, phi 1 plus I phi 2. And of course, I can either think of them as complex fields and their complex conjugate, or I can just think of, incidentally, this phi and this phi are the same thing. I sometimes draw it this way and sometimes draw it this way. That's one way of thinking of a complex field as a complex field. The other way of thinking about it is a pair of real fields, in which case we would say at every point in space we have a set of axes, one of which we call phi 1 and one of which we call phi 2, and at every point in space the field takes on some value. At this point over here, the field might be oriented, our complex scalar field might be located at this point. At that point over here, it might be located at this point. But in saying something like that, we're implicitly assuming that there's some kind of way of relating directions in this space at different points of space. Let's, just to get this idea and to pin this idea down, let's go back to the jump rope analogy. The jump rope analogy for the complex field is just that we have a string, a long string, could be a rope, and that rope is at every point free to move in two directions, up and down and right and left from my perspective over here. I should have brought in a rope. I always, Who wants to play jump rope? Yeah, okay, good. I don't know, this is not going to go very far. All we're going to do is swing the rope around, but okay, let's do it anyway. Yeah, oh, you take that in, good, okay. So this is a rope, which when was stretched out is like this, but it's actually free to move both horizontally and vertically. And then it has the capacity not just to vibrate, but to vibrate in a way that has some angular momentum. Now, in order to explain not to explain, but in order to describe the configuration of this string, I have to tell you not just how far from the origin now means the straight string when it's as straight as possible, not only how far it's been displaced, but at what angle it's been displaced. Right? So I have to describe both either a complex number at every point. Complex number could be x plus iy for the position of the string, or, thank you, or I could describe it either a pair of coordinates, a complex number, or an angle and a radius, any number of ways of describing it. But it's implicit in describing things that the coordinate axes, x and y, that I use over here on the string are parallel to the coordinate axis over here or parallel to the coordinate axis over here. So we have made an assumption that it is possible to compare angles at different points and say whether they're the same or not the same. It is not completely obvious that that's a good assumption. In fact, really honestly, when one takes general relativity into account in the motion of strings and so forth, it is not so obvious, and in fact it's not even true, that there's a unique way of comparing angles at different places. But we're not talking about angles in real space now. We're talking about angles in a fictitious field space, which is mathematically similar to the rotation of the jump rope, but we're talking about angles in a mathematical field space. And this situation comes up when we ask questions like, is the value of the complex field at one location the same as it is in another location or not? In order to answer that question, we have to compare angles in this, among other things, angles in this space at different points. Now here's what we know. For some field theories, namely those which have a concept of charge, that there is an invariance, a symmetry. And the symmetry corresponds to rotating the coordinates phi 1 and phi 2, rotating them to some new direction, or equivalently, what's equivalently is rotating the position of the field not in space, but in phi 1, phi 2 space. You either rotate the axes, or actually physically change the value of the field by rotating it. In either case, the coordinates of the field will change. So we could imagine a symmetry transformation of the fields, which can either, as I said, be described by physically changing the configuration or just changing the coordinates that we use to describe the field. And we know how to describe that. We can describe it trigonometrically, that phi 2 prime is equal to cosine of an angle and so forth. But we can also describe it in complex notation very, very neatly. The transformation that corresponds to rotation of coordinates can just be written phi prime, that's the value of the field after, or the value of the coordinates of the field after you've rotated the coordinates, is equal to e to the I theta times phi, the unrotated notation for the field, where theta is just the angle of rotation here. Now, I hope nobody gets confused between thetas and phis. Phis are fields. Theta is just an angle of rotation in this field space of the coordinates which describe the field. Now, this is an operation that we can do on a field. It corresponds, in the case of the jump rope, to going at every point in the jump rope and changing the angle by the same amount. By the same amount, that's the key phrase. By the same amount, theta is just a number, and it rotates the field in the field space sort of rigidly everywhere by the same amount. That's a symmetry, for example, of the Lagrangian that we studied last time, which, what was it? It was d mu phi star, d mu phi. Question?
Yeah, is phi prime relative to, is that this?
Phi prime, it's
relative to the green line, in which case we get.
Yeah, that's right. Phi could be the coordinates relative to the black line. Phi prime could be the coordinates relative to the blue line, green line.
Phi theta? And isn't it even minus phi theta? Because the angle's getting smaller when you rotate by positive theta.
Yeah, well, it doesn't, you may be right, but if it's invariant under multiplication by a phase like this for every angle, it includes negative angles and positive angles. So quite possibly for this particular setup over here, I may have inadvertently put the wrong sign here, but it doesn't matter for anything. Good, so let's change the orientation to conform correctly to the formula. You're probably right that I've rotated the coordinates the other way. All right, so phi prime, and besides which, I haven't told you which was phi and which was phi prime. So there's no way to compare it. I guess we would call, let's see, we'll call the coordinates here phi prime. Now I think we fixed it. And phi 1 prime and phi 2 prime. Okay, this is either right or wrong, and I don't really care. Good. Now, we studied some Lagrangians. We studied the Lagrangian, the derivative of phi star times the derivative of phi. These are complex conjugates of each other. We added, for fun, another term. I think it was minus mu squared phi star phi. And this Lagrangian is invariant under this operation. The reason is because if phi is replaced by phi prime, then phi star prime, or phi prime star, is e to the minus I theta phi. And furthermore, the same is true of the derivatives. Supposing I differentiate phi prime, the derivative of phi prime with respect to x, let's pick a particular coordinate with respect to x, is equal to what? Theta here is just a constant for my purposes right now. And so when I differentiate phi prime, I get nothing from differentiating the e to the I theta. That just stays there, times derivative of phi with respect to x. So the derivatives that appear here also themselves just get rotated by the same phase angle. When you multiply them by their complex conjugates, the e to the I thetas cancel. E to the I thetas cancel here. And so this is an example of a Lagrangian which is invariant with respect to phi goes to phi e to the I theta. Okay, now you might ask, what would happen though? Is it invariant with respect to rotations of this plane which vary from place to place as you move along? For example, we could ask exactly this about the rope. It really does have to do very deeply with the question of whether you can compare these angles at different places. To say that the Lagrangian is invariant under phase means that you don't have an invariant sense of what angle 0 means. You can rotate the whole picture, but comparing angle 0 at different places is meaningful. But supposing this Lagrangian turns out to be invariant under a stronger symmetry, a symmetry where you rotate the angle at each point by an arbitrary angle which might differ from point to point. In other words, let's investigate whether the Lagrangian we've written down is invariant under a symmetry where we allow theta to be a function of x. That means as we move along from point to point in space, we rotate the axes differently. If there is no good sense in which you can compare angles at different places, then we would expect this to be just as good a symmetry as when we rigidly rotate. So we can think about this as the difference between a kind of rigid rotation and a rotation which varies from place to place. Okay, also x here. Well, let's examine that question. First of all, let's look, let me remember that we're supposed to integrate this over space, and the full action would be integral d4x. Let's look at the various terms in this Lagrangian and see whether they change or not when we do such an operation. Well, what happens to phi star phi? That's an easy one. Phi star phi, phi gets multiplied by e to the I theta, phi star gets multiplied by e to the minus I theta. At each point separately, those phase angles cancel. So this term in the Lagrangian is fully invariant under these position-dependent, let's call them position-dependent phase rotations. There's another name for position-dependent phase transformation. It is gauge transformation. That is what a gauge transformation is. Or at least this is a special case of the more general concept. More general concept, any kind of symmetry, you can imagine doing it differently from point to point. All right? So this term, we could check it off. This term here is invariant. Red check means that that term is invariant. What about these terms which involve derivatives of phi? If this is going to show up anywheres, it's going to show up in questions having to do with how phi varies from place to place, and whether when we compare phi at one point with a neighboring point, whether this Lagrangian is invariant. So let's check. Let's calculate. All right, let's see, I think, do I want to switch the definition of phi and phi prime? I may, just to conform with my notes. No, I think I have it the way I want it. Okay, so this is the primed field. Here's the unprimed field. Let's calculate, and here's the, and yeah, you know what? Let's, right. Let's write the Lagrangian in terms of the primed variables. Primed, unprimed, what's the difference? We can just change, it's just changing names. That's just changing names of what we call the field variable. Here's the Lagrangian for the primed field. Let's work it out now. Since we know the relationship between the primed and the unprimed field, let's work out whether this Lagrangian has exactly the same form if we substitute for phi prime phi. All right, the first thing we have to do is figure out what happens to the derivative of phi prime with respect to x mu. That appears in the Lagrangian, but I want to rewrite it in terms of phi. All right, but now when I differentiate, I get two terms. I get one from differentiating this factor and one from differentiating this factor. The first term, well, let's take the first term to be the simpler one when you differentiate phi. That just gives you d phi by dx mu times e to the I theta of x. This doesn't worry me because I expect that when this is multiplied by the complex conjugate, it's going to go away. All right, but then let's take the other term. The other term, you differentiate e to the I theta of x and multiply by phi. All right, so what's the derivative of e to the I theta of x? That is I times the derivative of theta with respect to x times e to the I theta. I've used the derivative of an exponential is just equal to the derivative of what's in the exponential times the exponential itself. So both the terms have an e to the I theta. That's a good thing because that'll probably cancel when we multiply by the complex conjugate. But we now have this gradient or this derivative of the phase angle, derivative of the transformation phase angle. And that's not so obvious that that will cancel out. In fact, it won't. So let's rewrite now the Lagrangian in terms of phi instead of phi prime. It's just a change of variables. It's just a change of what we meant by the field. And let's see what we get. Now we get integral d mu phi star. Let's see. I should write down what happens to the derivative of phi star. The derivative of phi star, phi prime star, with respect to x mu, what happens to it? You just complex conjugate. That's equal to the derivative of phi star with respect to x, e to the minus I theta. That's the complex conjugate of this factor. And then the complex conjugate here is minus I d theta by dx mu times e to the minus I theta of x times phi star. All right, the minus came because the derivative, because the complex conjugate of I is minus I. All right, is everybody happy with this? If not, stop me now and I'll explain what's on the blackboard.
And put a star in the second term.
Star on which second term?
Yeah.
Here?
Yeah.
Where?
You just
Here, there's a star there.
Oh.
Yeah.
D phi d.
Phi star here, yeah, good. Phi star here, right. Okay, now, if I didn't have to worry about this term here, I would just multiply these two. If I didn't have any x dependence in theta, for example, if theta was independent of x, these terms would not be here, and I would just be multiplying this by this, and the e to the I phi's would cancel, and I would find out that this Lagrangian was exactly equal to the same thing, except replacing phi prime by phi. Okay? But it's not true now. Let's work out what we have. We have d by d mu of phi star times, let me factor out the e to the minus I theta, minus I d theta by dx mu times phi star. Now, I kept for last e to the minus I theta. Let's put it there. Now we have to multiply that by the complex conjugate, the derivative of phi, or the derivative of phi prime. That comes from here. Each term has an e to the plus I theta, which will cancel with the e to the I theta here. So that's good. That e to the I theta cancels as before. And what are we left with? We're left with d phi by dx mu plus I d theta by dx mu phi. Let's add back in this minus mu squared phi star phi. All right, so the cost of replacing phi prime by phi, by this position-dependent rotated phi, is some extra terms in the Lagrangian. And so the Lagrangian does not have the same form that it started with. It has a different form. It now has things in it. Now, theta is not really a degree of freedom. It's just an arbitrary angle that we chose to vary throughout space in an arbitrary way. But when we do that, the structure, the form of the Lagrangian changes. It's not a symmetry. It's only a symmetry if the Lagrangian would have come back to exactly the same form. So we can put a cross over this term. This term is not invariant. This term is invariant. Lagrangian we wrote down is just not invariant under this transformation. What does that mean? That means that if we that means, among other things, that if we did this operation on the field where we rotated it from point to point, we would change the energy of the field. We change the Lagrangian, we change the energy of the field, we change the momentum in the field. It just isn't the same configuration that we started with, and it's not a configuration that has the same properties. Now has different equations of motion, different Lagrangian. All right, so our first conclusion then is that the Lagrangian, the complex scalar Lagrangian, has an invariance under rigid phase rotations, but it is not invariant under gauge transformations. Gauge transformations mean these non-rigid rotations where you vary differently at different points. Let me stop there and take any questions that come up, because this is the essence and the heart of modern field theory, basically, this being the simplest example. Yes?
Getting a little confused by your notation there. D mu, is that the same as d by dx mu?
Yes. Yep. I will write down again a whole bunch of equivalences. d phi by dx mu is equal to phi mu is equal to d mu phi. Did I have any other names for it? I don't think so. But yes, these are things all mean the same thing.
Okay, but subscripts and superscripts?
Subscripts and superscripts are different. Now, how are they different? They're not different if we, let's see, it's the time component which changes when we, I think, yeah, right. That may mean, I may be off by a sign here. This may be possibly a minus sign there, but that's not the important issue here.
That second one doesn't have any imaginary components, right? Because there's supposed to be complex conjugates you multiply.
Sorry, which, yeah, this has no imaginary component to it, because it's something times its complex conjugate, but it still does remember this, right.
Yeah, it looks like it can sort of be combined with mu squared or something.
No,
With-
mu squared is a different quantity.
Oh,
It's not
well,
an
No,
yeah.
but I mean, after you
Of
get
course,
rid
everybody realizes this mu has nothing to do with the mu in the these
right,
meters,
right,
right?
right.
I probably should call it m
When you
squared.
get rid of the imaginary function, are you going to continue on this? You going to continue to expand this out, or?
Oh, if you like, I can. Yeah, let's do it. All right, so this is d mu phi star. Oh, I guess one of these should have upper indices, shouldn't they? I'm not sure how to do that. Okay, I know what to do.
Do you learn anything if you expand it out?
No, but let's do it anyway. D mu phi, and then d mu theta. Oops, d mu theta. Do you learn anything if you expand it out? I don't see anything.
When you expand it out, the first product, it just has two terms because the imaginary parts go away.
No. That's, all right, we will learn something. D mu phi star times d mu phi. Now that's just the good old Lagrangian that we might have expected if there was a symmetry. Then, of course, there is minus I d theta by dx mu let's see, we're taking the cross terms now. Let me write the cross terms carefully. The two cross terms. They don't cancel. Are you asking whether they cancel?
Yeah.
No, they don't.
They do have an imaginary
No,
part.
let's see what they have. They have minus I d theta by dx mu. All right, first of all, they multiply d theta by dx mu, both of them. This times this, and this times this, the two cross terms. All right? Both of them have i's in them. And one of them has, let's see what it has. It has phi times d mu phi star. And then it has minus phi star d mu phi. And then finally we have minus I times plus I is plus d mu theta d mu theta. It's just the square of the sums or the differences of the squares of various derivatives of theta times phi star phi. Okay? Now, this does not cancel. Phi derivative of phi star is not the same thing as phi star times the derivative of phi. These two are complex conjugates of each other. When you subtract them, you get something pure imaginary, and that cancels this I here. Now, do you remember this quantity?
It was something that was invariant, conserved, I guess.
It was the current. The current, J mu. Its time component was the charge density. Its space component was the current density. Okay? Together, they satisfied the flow equation, the continuity equation. Right. All right. Okay, so we at least see something familiar. And then this term over there is just whatever it is. It contains a phi star phi, which I suppose we could combine with this one, minus m squared phi star phi. Good. All right, so yeah, we did learn something, I think, by we discovered this term here. Good. So answer is no cigar. This Lagrangian is not invariant under such a transformation. But if that was the end of the story, of course, we would go home and say this idea of gauge invariance is not important, and 75 years of physics down the drain. All right, so let's see if we can force it to be invariant. But to do so, we have to add another collection of fields. To do so, we have to add another collection of fields into the brew, and to give those fields also transformation properties under the same transformation. We're going to have to invent more fields and more transformation properties to go with them in order to make this a symmetry. The new fields that we're going to invent are our first experience with vector fields. Of course, we have some vector fields. Anytime we differentiate a scalar field, it's a vector field. But now we're going to invent some new fields which are, how to say, primordially, they are vector fields from the beginning, fundamental fields. They're not derivatives of any other fields. And we're going to give them a name. We're going to call them A mu. Now, A mu has 4 components. I'm going to tell you right now what they correspond to so that we won't be working in the blind, so that I won't just be doing mathematical formalism on the blackboard. If you know anything about electromagnetism, you know that the electromagnetic field tensor, sorry, I won't even use that word, that the electric and magnetic fields can be written in terms of vector potentials and a scalar potential. I won't write them down now, but there are 4 quantities, the 3 components of the vector potential, and the 4th is basically called the electrostatic potential. And those 4 quantities form a 4-vector. The electrostatic potential being the time component and the vector potential being the space components of a 4-vector. That's what these things are. The time component being, being the electrostatic potential, and the other 3 components being the space. Do you remember, for example, what the magnetic field is in terms of A, in terms of the space components?
Del cross curl.
Yeah, it's the curl of A. And the electric field, something else that can be written in terms of these. And we'll come to them, what they are. Okay, so we're going to invent 4 more fields. Now these fields, unlike theta here, theta wasn't a dynamical field. It's not something which has an equation of motion. It was just a transformation that we decided to do. We picked it at will. And when we picked it, we found out that this was not a symmetry unless theta was constant. But now we're adding more fields. Okay? And I'm going to add this field, and I'm going to assume that it also transforms under the same transformation. Now, what do I mean by that? I mean there's some transformation which involves all of the variables. Just in the same way that if I rotate the coordinates of one particle, I also need to rotate the coordinates of another particle, and so forth and so on. There may be many degrees of freedom, all which transform under the same transformation. So we're going to assume, we're going to basically postulate that A also has a transformation property, or must have a transformation property, whenever we do such a transformation. And the transformation property is going to be this. It's going to be A mu, let's call it the, hold on a second, I've screwed up my notes here. I seem to have notes from several different lectures all mixed up together. Yeah. Yeah, before we talk about the transformation property of A, let's talk about how A fits into the Lagrangian. A is another variable which has an equation of motion. It will also have waves. Those waves describe electromagnetic waves and so forth. And A also has a Lagrangian of its own. Plus, there are interactions between A and phi, which means there are things in the Lagrangian which will involve both A and phi. So let's go back to the phi prime Lagrangian. Let's go back to the phi prime Lagrangian. Our variables now are all our phi prime, phi complex conjugate prime, and I'll also call the vector potential, the 4-dimensional vector potential, A mu. I'll call it prime for a moment. These are the primed variables. The unprimed variables will be obtained from these by some transformation. And the Lagrangian for the prime variables, I'm now going to modify. I'm going to modify it to d mu phi star prime. Let's put the star on the outside. Star out here. D mu phi prime. And now I'm going to add something. I, a constant called E. That constant will ultimately appear as the electric charge of a charged particle. But it's just a constant in the Lagrangian now, a numerical number, times A prime mu phi prime. What I've done is I've replaced just derivative of phi by a new thing, which is the derivative of phi plus IA times the vector potential times phi. This is a new thing. It's actually called the covariant derivative of phi, but for the moment, it's just a new object. And we're going to multiply that by, notice that it's complex conjugated. Okay? When you complex conjugate, you got to complex conjugate everything, phi and I. A is real. A is real by assumption, and that gets multiplied by d mu phi prime plus I.e. A prime mu phi prime plus or minus m squared phi star phi. So I've modified the original starting Lagrangian by replacing the derivative of phi by a new thing, derivative of phi or derivative of phi prime plus I.e. A times phi prime. Sometimes people write this by saying just replace derivative with respect to mu by derivative with respect to mu plus I.e. A mu. Just replace the derivative operation by derivative plus multiplication by I.e. A mu. Right? So sometimes one says that this is a new replacement for the derivative, which we call the covariant derivative. Just a name. This covariant has nothing to do with the covariant from, yeah.
Are the phi's at the very end of that, is that phi or phi prime?
Oh, sorry, phi prime.
At the very end.
Good. It actually doesn't matter, but right. Okay, right. Good. All right, now supposing we carry through the same set of operations, and in other words, the same set of operations where we're going to replace phi prime by e to the I theta x phi. What are we going to get? Well, exactly the same thing is going to happen, and this derivative here is going to get replaced by d mu phi. Where is it? Plus, I'll do the complex conjugation at the end, plus I d mu theta, oops, lower d mu theta times phi. That's what happens to derivative of phi prime. It just becomes derivative phi plus I d mu theta times phi. Okay. But now we have to add plus I e a prime mu times phi. Is this obvious what I've done, or do I need to explain it? I think I may need to explain it a little more. All I'm doing is replacing for phi prime e to the I theta phi. When I differentiate theta prime, I'll get the extra term I d mu theta times phi, just as I did there. Oh, incidentally, this also gets multiplied, I guess, by e to the minus I theta, all pieces. And this should be complex conjugated. We can complex conjugate it by just all right, stop me now if you don't understand what I did. I don't understand what I did because I lost an I. Yeah. Just complete substitution. Wherever I saw phi prime, I stuck e to the I theta times phi. That, complex conjugate, and then add in the new term, the new hypothetical term that I've added into the Lagrangian for fun, for the fun of it, just to see what happens. That's one factor. The other factor will cancel the e to the I theta. This will cancel as before. And what we'll have then is just the complex conjugate of what's here, d mu phi plus I d mu theta times phi plus I e a prime mu phi. And let's forget the m squared phi, right, minus m squared phi star phi. Notice what's happened. All that's happened.
There's such a thing as a super mu?
Yeah, we're A super mu, good. This is not A1 mu, it's just A prime mu, super mu. Yeah, if this has lower indices, then the right-hand side has to have upper indices, and that's it. Okay, now look what's happened. What's happened is the Lagrangian sort of has changed form on the one hand. It changed form what it started with in that it now has this new term, but there's another sense in which it hasn't changed form. If I combine d mu theta with a mu, if I combine those together with a prime, in other words, if I take d mu theta plus a as a plus a prime, and I call that a. I just call that a, unprimed, then this has exactly the same form as it started with, except both phi and a, we've dropped their primes. It has exactly the same form. And so that tells me that if I want to maintain the symmetry, I had better postulate a transformation property of A, namely that you simply add the derivative of theta to it to define the new field after transformation. So, to have a symmetry, we add another field into the brew, A mu prime, and that's equal to A mu plus I, no I, d mu theta. This is the full transformation property, or the full transformation structure of the three fields phi, phi prime, phi star prime, and A. Actually, how many fields are there? 2 here, 2 here, and 4 more here. 6 fields here, 6 independent components.
The last symbol there, is that a phi or a theta?
Where?
On the
Theta, theta.
Okay, is that a function of x or not?
Yeah, it's a function of x. Otherwise, how could you differentiate it?
Right. Yeah, but it's not a function of time.
It could be. Yeah, no. Derivative with respect to mu means derivative with respect to everything.
Okay.
So we're not just comparing reference frames at different points of space, also in time. Right. We're imagining that our coordinates in this angular space can be rotated in space, and they can also be rotated. They can be rotated from point to point in space and point to point in time. Okay. So let's just go through it again. We started with a new Lagrangian, a new field theory that contains a new set of fields A that enter into the old Lagrangian in this new way. Then we carried out the change of variables from phi prime to phi, and we discovered that basically what it does is it keeps the same form for the Lagrangian, except that we have to modify a prime and add to it the derivative of theta. This is the full structure of a gauge transformation. And if we make these substitutions, into the original Lagrangian, then the form of the Lagrangian does not change. And we can write that this is equal to, I'm just going to replace this, exactly the same thing, except with all the primes dropped. All right. This is equal to same thing without primes. That's the idea of a symmetry. If the Lagrangian has exactly the same form, both before and after the transformation, then you say there's a symmetry. So this new field theory, whatever it is invariant under local gauge transformations. Local means that the phase parameter here can depend on position.
Is that gauge covariant, or is that you're using covariant?
Gauge invariant. The Lagrangian is gauge invariant, or the action is gauge invariant.
Okay.
Invariant.
The I thing, that's e to the 1,
E to the 1.
IEA.
I,
You left up, you
that's
left
A prime.
Well, whatever, but the e is just e to the 1?
Yeah.
That's not,
It's
That's
oh,
not-
charge.
Oh, that's not E, that's not the mathematical symbol 2.7128, whatever it is. This is the electric charge of some particle. Now what particle? The quanta of the field described by phi. But that's yet to be proved, that in any sense that this has...
Transformation, you should,
Yeah.
you left out the E in there. It should be, I think you should
Oh, you're right.
divide.
1 over E, 1 over E. You're right. 1 over E.
And maybe that should be a minus in front of that portion,
Which one?
in that transformation, right beside the 1 over E.
I thought it was plus. Let's
No,
see.
because he sort of worked it backwards, and so it
I thought it was plus.
So maybe that's it.
Maybe,
yeah, I think.
no, I think you're probably right. I think you may be right, yeah. Yeah, I think we had that A, yeah, you're right. A was equal to A prime plus the derivative, I think. Yeah,
Right, okay.
yeah, 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 yeah. Good. I think we have it right now. Okay. So what we've discovered up till now is we can force, if you like, we can force a field theory to have this new kind of invariance where you transform things from place to place, not just rigidly. In fact, the only real symmetries of nature are gauge symmetries like this. All others are not really symmetries of nature. Not yet. All right, now, what I haven't indicated here is whether there's other terms in the Lagrangian governing A, for example. The phi part of the Lagrangian, we've seen what the phi part of the Lagrangian corresponds to. It's out of phi, oh, incidentally, yeah, same thing without primes. Notice how A enters into the Lagrangian. What will happen to this form of the Lagrangian when we put A prime in, or A in? This will get replaced by A. So in fact, the Lagrangian, which I could write as having, is a plus, I think it's plus E times A prime. This whole thing just becomes becomes A. Now, I don't know how familiar it is. Did I leave out E? I think I left out E. Yeah, E. E, A mu. I don't know whether this strikes a bell or rings a bell to you or not. Do you know what the Lagrangian for a current in an electromagnetic field looks like? An electric current in an electromagnetic field? In particular, a magnetic field.
A dot V in it.
No, not A dot B. Not A dot B.
A dot V.
This P goes to, momentum goes to momentum less E times the vector potential.
This is true, and that's one way of seeing it. But if we're talking about a uniformly flowing, a current of some sort, not an individual particle, what is the coupling of a current to the electromagnetic field? Okay, I'll tell you right now.
A times the current, right?
What is it?
It's A times that current.
A times that current. A dot J. A dot J. We're going to come back to this. We're going to come back to this. A dot J. And more generally, this would be the case if there was only a space component. This would be the coupling of a magnetic field to a current. Well, that's about what we see here. We see J and we see A. So we see the pieces plus a time component piece. We see the pieces that are traditionally the interaction between electric and electric charges or electric currents and electric currents and the electromagnetic field. Electromagnetic field is best described in terms of the vector potential, and the electric and magnetic fields are things that we build up out of the vector potential. Okay, now let's talk about the electromagnetic field when there are no charges and currents. In other words, let's forget about phi. Let's forget about phi and ask what kind of theory describes A by itself. What we're talking about now is electromagnetic waves propagating in the absence of charges. Supposing we just forget phi. Phi is the thing which describes the charged currents. It's the thing in quantum mechanics which describes the charged particles. The charged particles are quanta of this field. But let's forget charges. We know that electromagnetism has an interesting non-trivial behavior even far from where there are any charges, namely electromagnetic waves propagating through empty space. So there must be some dynamics to the electromagnetic field which is even there in the absence of charges. So it's not this, it's something just involving the electromagnetic field itself when this field phi is equal to 0. Oh, this, incidentally, this would become a squared here, a mu. So what shall we say governs the electromagnetic field by itself? Well, I would like to maintain this gauge symmetry. If I'm going to go to all of this effort to invent A just to make this Lagrangian gauge invariant, I certainly don't want to destroy that gauge invariance by not having the electromagnetic field Lagrangian by itself be gauge invariant, by not having it. So we want the Lagrangian that we make up, let's call it L, that part of it which depends on the vector potential in various ways, the vector potential and its derivatives. Right? We want that Lagrangian also to be gauge invariant. So that brings up the question then, what kind of combinations can I make up out of just the electromagnetic, out of just A by itself, the 4 components of A, what kind of combinations can I make up, in particular, out of the derivatives of A? I'm mostly interested in the derivatives of A. It's typically derivatives of fields which enter into Lagrangians. There may also be things without derivatives, but Lagrangians' most important thing is dependence on the velocities, the derivatives. So what kind of thing can I make out of the derivatives of A that itself is gauge invariant that might enter into Lagrangian?
With the same gauge invariance that you have up there. In other words, A transforming the same way.
Yeah, that's right. With A transforming in this way. Right. In other words, invariant under A goes to A minus 1 over E times the derivative of theta for arbitrary theta. Any theta is allowed. You pick it. We want the Lagrangian to not change when we do this operation. Let's put some indices in here. Okay. All right. Let's see if we can figure out. Let's look at the various derivatives of A. There are 4 components of A, and there are 4 distinct derivatives that we can do. That means there are 16 derivatives of A that we can concoct. Derivative with respect to x of A sub x, derivative with respect to y of A sub x, and so forth. There are 16 of them, since there are 4 components of x and 4 components of A. They can all be summarized in the form d nu A mu. Mu can go from 0 to 3. That's 4 components. Nu can go from 0 to 3. And so this is just a convenient way to represent basically a matrix of 16 independent derivatives of the 4 components of A. Let's see what happens to this when we make a gauge transformation. When we make a gauge transformation, A mu will go to A mu minus 1 over E d mu theta. So this will go to d nu of A mu minus minus 1 over I, 1 over E d mu theta. In other words, it will pick up an extra term. The change in d nu theta will be the extra term, is the extra term, will be minus 1 over E d nu d mu theta. D nu d mu theta. What does this mean? This means the second partial derivative. First you differentiate with x mu, and then you differentiate with respect to x nu. Everybody understand what the symbol is? D nu d mu theta? It's the second partial derivative of theta with respect to x nu and x mu. Okay, that in itself suggests, if you've fiddled with these things at all, it would immediately suggest what the invariant quantity you can make. Let's look at the related quantity. This could, for example, be, if nu was 1, let's take the case nu equals 1, mu equals 2. That would mean derivative with respect to x of a sub y, for example. 1 corresponds to x, y corresponds to 2. There's another quantity which also has an index x and an index y in it, and it's sort of the opposite. It's dy ax. Okay? We could represent the matrix of those variables as d mu a nu. All right, so if nu is 1 and mu is 2, then this could be dx of ay, and this would be dy of ax. But each one has 16 components. What happens to this quantity when you make a transformation? Well, all I have to do is swap mu and nu. I don't have to do much work. It goes to d mu a nu. All I've done is interchange mu and nu. And then minus d mu a. d nu theta. All I've done is interchange mu and nu. Okay, so d nu, this goes to minus d nu d mu theta.
What happened to E?
Yeah, divide by E.
Yes, 1 over E. Good. Now it's pretty clear what to do to make something which doesn't change under a gauge transformation. First of all, the theorem. The theorem is that the order of differentiation of a variable, of a function, is immaterial. The derivative with respect to mu times the derivative with respect to nu is the same as the derivative interchanged. All right? For example, the derivative with respect to x of the derivative with respect to y of theta is the same as the derivative sub y, derivative sub x of theta. Order of operations for derivatives doesn't matter. dx dy is the same as dy dx. So that means that d nu d mu theta is the same as d mu d nu theta. Supposing I subtract these two things and define a new quantity, d nu a mu minus d mu a nu. That's not 0. We're not subtracting the same thing. We're not subtracting a thing from itself. We're subtracting, for example, dxay from dyax. That's not 0. But what happens to it under a gauge transformation? Nothing happens to it because the shift cancels out. The change in the two of these is the same, and when you subtract them, the change cancels out. So under a gauge transformation, this just goes to itself. d nu a mu minus d mu a nu, how many such quantities are there? 16 to begin with. 16. There are 16 quantities which are all invariant. All 16 of them are invariant under gauge transformations. Now, there actually aren't 16. Or at least there aren't 16 non-trivial ones. 10 of them, 10 of them? Well, first of all, 4 of them are 0. All the ones in which nu and mu are the same. We can make a matrix out of these. We can make a matrix out of these, a 4 by 4 matrix. Label the matrix entries 0, 1, 2, 3, 0, 1, 2, 3. And then in each entry, we could put the appropriate d nu a mu minus d mu a nu. I think you get the idea. What happens on the diagonals here? There's 0. This is d1 a. This is d0 a0 minus d0 a0. Here we would have d1 a1 minus d1 a1. So all the diagonal entries are 0. It's antisymmetric. Yes, it's antisymmetric, which means when you interchange mu and nu, it changes sign. So first of all, it's 0 along the diagonal. There are some entries off the diagonal. For example, over here, we would have, I think, d1 a0, I think, minus d0 a1. What would we have down here? The opposite with the opposite sign, because when we interchange mu and nu, the minus sign here causes it to flip. So whatever we have above the diagonal here, we have exactly the same thing below the diagonal, except with the sign changed. So there's no use of keeping track of the things above the diagonal and below the diagonal separately. They're so closely related, they're just opposites from each other, that they're not independent. And so how many independent quantities are there? There's all the ones above the diagonal. That's it. 1, 2, 3, 4, 5, 6. 6 independent derivatives of this type that we can form. 6 independent components of this antisymmetric object. What are those 6 independent components? I mean, I will tell you now. I don't want to hide it and jump out and surprise you with it. The 6 independent components are the 3 independent components of the electric field and the 3 independent components of the magnetic field. In fact, we could put them up in here. The 3 independent components of the electric field are up in here. I'll be more precise about them later. And the 3 independent components of the magnetic field are here. For the moment, we're just counting how many independent quantities are there. 6. How many independent components of the electric and magnetic field are there? 6. It sounds like they may be related. In fact, they are the same thing. But the precise connections between them we'll come back to. All right, this object here, d nu a mu minus d mu a nu, which is made up out of first derivatives of A. There's a symbol for it and a name for it. It's called the electromagnetic field tensor. Okay? It's called the electromagnetic field tensor, and it consists of the components of electromagnetic field, E and B, and the symbol for it is F nu mu. So F is just a complex of 6 objects that forms an antisymmetric tensor whose components are really in disguise the electric and magnetic fields. We'll come back to them. But now we have something that we can build a gauge invariant Lagrangian out of. In fact, this is the only thing which is gauge invariant and made up out of the first derivatives of A. What kind of thing would we like to have in a Lagrangian for A? Well, Lagrangians are usually functions of the variables in their first derivatives. In fact, that's always the case. Lagrangians are functions of the variables in their first derivatives. Which variables are we talking about? We're talking about the a's. Anything which doesn't have derivatives in it, a squared, anything like that is not going to be gauge invariant. It just won't. A will change under a gauge transformation, and any simple function of a that doesn't contain derivatives will not be gauge invariant. The only thing that's easy to make up that's gauge invariant that contains a and its first derivatives is f mu nu. That's it. That's the only gauge invariant quantities that there are which contain no more than first derivatives, and that's it. So what can you do to make a Lagrangian that's quadratic in derivatives? Supposing we want to stick to this pattern of things which are quadratic in the derivatives and which is Lorentz invariant. Let's come back now. There's another invariance that we wish to keep track of, and that's Lorentz invariance. To keep track of Lorentz invariance by now should be very easy. All we have to do is contract indices, upper and lower indices. As long as all indices are contracted correctly, then Lorentz transformations will be a symmetry of anything that we make. It's pretty obvious there's only one thing that we can make. It's f nu mu, f nu mu. This is basically sums and differences of squares of the components of f. I'll tell you exactly what it is. It's E squared, the electric field squared, minus the magnetic field squared. E squared minus B squared. Now we're going to come and we're going to study the nature of this field tensor and its relation to the electric and magnetic fields in more detail, but I'm sort of outlining and sketching where we're going. That we will, okay, so let's summarize. If we wanted to have this peculiar gauge invariance, then we were forced to introduce a new variable called A. A itself had a transformation property, and it entered into a new structure called the covariant derivative. Where's the covariant derivative? D mu plus I E A mu is the covariant derivative. Then we discovered that if in the original Lagrangian we replaced all derivatives by covariant derivatives, that's the operation, replace all derivatives by covariant derivatives, and at the same time allow the vector potential to have its own transformation property, then the Lagrangian was invariant under these gauge transformations. So that's a kind of pretty thing, that there is a Lagrangian that we can write down that generalizes the original Lagrangian, which has this improved symmetry, this more powerful symmetry, or this bigger symmetry, where you can vary the phases from point to point in space. Well, then we said, good, now let's talk about A by itself. We've motivated why A has a certain gauge transformation property. Now let's ask, can we make Lagrangians for A by itself which have this gauge transformation property, that they're invariant? And so we looked around for expressions which would not transform when you make a gauge transformation. In fact, we looked around for things that we could make up out of the derivatives. These are the 16 possible derivatives of A. And the obvious answer is the antisymmetric quantity d nu a mu minus d mu a nu. For that, this extra piece which gets induced by the gauge transformation cancels. So we found a gauge invariant, f mu nu. Anything that we make out of f mu nu will be gauge invariant, but not anything that we make will be Lorentz invariant. Just f mu nu by itself is not Lorentz invariant. It has open indices hanging around here. That's what I mean when I say it's not invariant. Yeah, it's not a scalar. It's not a scalar. It has open indices here. It has components. So it'll transform in various ways. But if we square it, and contract the indices in the right way, it will become something which is Lorentz invariant, and in fact it is just E squared minus B squared. It's not obvious that this is Lorentz invariant, but it is. E squared minus B squared is a quantity which is the same in every Lorentz frame. If we have an electric field someplace and a magnetic field, and we look at it from a different state of motion or a different angle, the electric and magnetic field components will transform. In fact, if we view an electric field from a moving frame, we'll typically see a magnetic field. If we view a magnetic field from a moving frame, we'll see an electric field. But whatever E squared minus B squared is, it's the same in every reference frame. That's the content of this expression. E squared minus B squared is invariant because all the indices are properly contracted. So now we have a candidate for the action of the electromagnetic field itself. We're not going to work out the equations of motion tonight. We'll do that another time. But I'm showing you the logic that went into to the idea of gauge symmetry. Well, let's continue. That's really, in a sense, enough for one night, isn't it?
Are you going to go into what's conserved because you have a symmetry? Or
Yes. Well, not tonight, though, but I may. I mean, yeah, I'd like to do that. Yes.
Yeah, can you go back to the analogy of the spinning rope and describe, if it's possible to describe A in regards to that analogy?
Well, I'll tell you that no, I can't do that at this moment because the analogy involves general relativity. Let's put it this way. In the rope analogy, these variables phi are actually coordinates of positions of the rope. So what we're talking about when we make these kind of transformations is coordinate transformations which vary from place to place. Coordinate transformations which vary from place to place are the material of the general theory of relativity. So until we would come to the general theory of relativity, that jump rope would not look gauge invariant. But it is gauge invariant when gravity is taken. But this is beyond, right now, beyond the level of the course at the moment. If and when we get to study general relativity, remind me to come back to this, and we can see how the jump rope also has its own gauge invariance, but not now. It's not the vector potential would be certain components of the gravitational field. Certain components of the gravitational field, which are there in the general theory of relativity, would become the analog of the vector potential. So it's a correct question. It's a good question, but it's beyond our level at the moment. All right, I think I'm just going to go on a little more and tell you a totally different way, which of course is secretly exactly the same way, of thinking about the electromagnetic field and its interaction with particles. This is the electromagnetic field and its interaction with charged wave fields. Phi is a charge-carrying wave field. That's the language one would use, or a charge-carrying scalar field that carries charge in the sense that waves of this field constitute electric charge densities and electric currents. And here we see the basic interaction A dot J, which is the hallmark of the interaction of charges with the vector potential. Of course, we might, now, when we study quantum mechanics, the particle field duality or the particle field complementarity, or whatever Bohr wanted to call it, tells us that all fields are associated also with particles. And in fact, the phi field is associated with charged particles. But we don't need to study quantum mechanics to figure out how to describe how charged particles interact with the electromagnetic field. We can just go back to the basic particle description of charges and ask in that language, the original particle, classical particles with carrying charge, how do they interact with the electromagnetic field? And so I want to completely change gears and go back to classical particles in the special theory of relativity. Classical particles, the Lagrangian for classical particles and the special theory of relativity, and then show you how the electromagnetic field correspondence, and in particular, we'll also see the idea of gauge invariance. Takes on a different form, has a different flavor to it, but it's the same invariance. Okay, so let's think of a world line of a particle. Here's the world line of a particle. The world line has to be chosen subject to the rules of the principle of least action. And so our first question is, what is the action of a moving particle moving in the special theory of relativity? For the moment, let's forget fields. No fields in the problem, just a free particle. Well, there's really only one invariant that we can make for a trajectory that in any way looks anything like an action. The natural quantity to identify with a trajectory is the length of the trajectory. The length of the trajectory is the relativistic length of the trajectory. The relativistic length of the trajectory is the natural quantity to identify with the action. In any case, it's a candidate. And the reason it's a good candidate is because it's invariant. It's invariant. The proper time, I should say the length of the trajectory, I mean the proper time along the trajectory. The proper time along the trajectory is basically the action of a trajectory of a particle. Well, not quite. You'll have to multiply the proper time along the trajectory by the mass. And for reasons which are pretty much conventional, there's a minus sign. I hate these things. Have we run out of them? Let's see. Minus m, the mass of the particle, times the proper time between the initial point and the final point along the trajectory. But what's the proper time? Well, let's start with the proper time along a little piece of trajectory. That's d tau squared is equal to dt squared minus dx squared plus dy squared plus dz squared. I'm just going to write dx squared here. In fact, that stands for dx squared plus dy squared plus dz squared. Let me write it out once in full. Minus dy squared minus dz squared equals dt squared minus dx squared. And dx, I suppose I could put a little arrow over this. Dx squared. All right. That's dt squared. That's the proper time squared of a small little interval. There are some speeds of light which would go in here. If we had speed of light, where would they go? I'm going to leave them out. They don't add anything to the discussion at this point. Okay, so this is d tau squared, and d tau, the actual proper time along the trajectory, is just the square root of this. So let's get rid of the c squares because we're grown-ups and we don't need to take the speed of light to not be equal to 1. And d tau is equal to the square root of this. The total path length, or the total proper time along the path length, is an integral. Integral from the beginning to the end along the trajectory of the square root of dt squared, and I'm just going to write minus dx squared, but please keep in mind that that dx squared stands for dx squared plus dy squared plus dz squared. Okay, that's the action. Now what on earth does this mean? The square root of the square of a differential. All right, first of all, what it means is chop up the trajectory into little pieces, calculate the square root of dt squared minus dx squared along the trajectory for each little piece and add them up. Basically, that's all. Add them up. That's what the symbol means. But we can make it look like a more conventional integral by dividing inside the square root, and then multiplying out here. I've basically multiplied and divided by dt. But if I put a dt under the square root, it becomes dt squared. All right, so what's in the square root here? What's in the square root is the integral, what's in the square root is 1 dt squared minus over dt squared, 1, minus, now what's the x by dt? It's the velocity. This is the square of the velocity. The square of the three components of the velocity summed. The x squared plus vy squared plus vz squared. So this is just, let me call it x dot squared. Dot means derivative with respect to ordinary time, not proper time. X dot squared, and of course it stands for x dot squared plus dy dot squared plus z dot squared, and I could also call it just v squared if I wanted. But I'm going to leave it there as x dot squared. Times dt.
Or you call it 1 over cosine hyperbolic?
No, I don't want to call it nothing. I just want to express it in terms of the velocity itself, minus m. Well, now I have a thing which looks like a Lagrangian. I should put the minus m on the inside. Let me put it on the inside in here. And put the minus sign also, minus m square root of 1 minus x dot squared. Lagrangians are actions are always integrals over Lagrangians, integrals with respect to time of Lagrangians. Now, we're not talking about field theory. We're just talking about the motion of a particle. So there's no integration over space. The degree of freedom now is just x. X, y, and z of t. The position of the particle as a function of time is the degrees of freedom. Here's a Lagrangian, which depends on velocities. It happens and doesn't depend independently on x. It only depends on x dot. Well, this is the kind of Lagrangians we've seen in the past. It's a little bit unusual. Instead of having an x dot squared, it has a square root of 1 minus x dot squared. But it falls within the class of Lagrangians which depend on the velocities and the coordinates. So it is a special case of a conventional Lagrangian. Let's use that, first of all, to calculate the momentum. What's the formula in terms of a Lagrangian for the momentum conjugate to x? Anybody remember? Derivative of the Lagrangian. This whole thing is Lagrangian here. Derivative of the Lagrangian with respect to x, x dot. All right, so now we get to try out our skills at differentiating. This is x dot, let me put y dot squared plus z dot squared. Okay, anybody good at differentiating? Equals. There's a minus m, and then we have to differentiate a square root. That gives us a square root in the denominator with a 2, square root of 1 minus, now let me call it v squared, x dot squared plus y dot squared plus z dot squared. And then we have to differentiate the argument of the square root with respect to x dot. Right? So that gives us a minus, another minus sign, a 2, and an x dot. The 2's cancel, and we get m times x dot, or better yet, m times the x component of the velocity over the square root of 1 minus v squared. I think we saw that before. We have studied this, have we not? Right. This is v squared over c squared if we were to put the c's back in. Well, that's nice. We see that the canonical momentum is just the momentum. The relativistic momentum, mass times velocity, with the Einstein correction, square root of 1 minus v squared over c squared in the denominator. What about the energy? What about the energy of the particle? The energy is the Hamiltonian. So if you have to, go back to your classical mechanics, but I'll tell you what the answer, I'm going to just tell you the answer. It's a little bit of algebra that goes into it, but I'll tell you what you have to do. The Hamiltonian of a system is the sum over the degrees of freedom of the velocities times the momenta minus the Lagrangian. Do you remember that formula? All right. So we have this. There's only one coordinate now, or three coordinates to be more precise. Three coordinates, x, y, and z. So for example, one of the terms will be x dot, that's q dot, times p sub x times m v sub x over the square root of 1 minus v squared over c squared. And then we have to subtract off the Lagrangian, which is plus m square root of 1 minus v squared. Okay, a little bit of algebra, not much, will convince you. Another factor of, yeah, let's get rid of the factors. Let's get rid of the c's. You're right. Let's just get rid of them. Yeah, because I've been loose in the coefficients of c here in other places. Let's just leave c equal to 1. This isn't so hard. This is x dot times vx is vx squared, right? Of course, there's also contributions from y and z. So this vx squared will become m vx squared plus vy squared plus vc squared. We should have added up the three terms. This just becomes mv squared, all three components, plus m, so let's see, so what is this? Let's put them over a common denominator. Let's put them both over the same common denominator, square root of 1 minus v squared. Let's get rid of the square root here. The v squares cancel, and we just get m over the square root of 1 minus v squared. Have we seen that before? Yeah. That's the energy. If we wanted to give it proper units of energy, when the c's are in there, it would be mc squared over v squared over c squared. And that would be the energy of the particle. All right, that's the canonical formulation of a particle in special relativity, not under the influence of any force field. All right. The question is, what happens when we include an electromagnetic field? Now, I'm getting tired, so the question is, yeah, let's see if it's rather easy, but okay, let's do it. I don't want to stop here because we're going to be gone for a week, and I guess I'd like to finish the line of argument and then have everybody study it in some detail. Suppose there's an electromagnetic field. An electromagnetic field is described by a vector potential A mu. So let's suppose there's a vector potential or a four-dimensional vector potential A mu. How can I combine it with the particle to make an action that involves the particle moving in the electromagnetic field? I'm not talking about the action of the electromagnetic field now, just the particle, the influence of the electromagnetic field on it. So what can I do with an A mu and a particle trajectory to make something that involves A mu and the particle trajectory, which is Lorentz invariant? Well, there's not too many things. Well, first of all, you could think of an infinite variety of things, but most of them would be exceedingly complicated. There's one simple thing that you can write down. Anybody know what it is?
A dot v.
Well, this is a 4-vector. That's a 4-vector. So we don't want to use a conventional velocity, dx dt.
A dot p. A dot p.
P is not a thing that you usually put in Lagrangians. We usually put in, all right, but let's, there's a simple thing. Instead of A dot V, instead of A dot v, which is on the right track, let's try a times, not v mu, but dx mu by d tau. But wait a minute, that's okay. This is an interesting quantity, a mu times dx mu by d tau. This is a 4-vector, dx mu by d tau. But this is not conventional velocity, and it looks a little bit awkward. But let's take the action. Let's try to use this in an action. What's the natural thing to do with this? The natural thing to do with it is to integrate it along the trajectory. But do you integrate it dt? And if not, why not? The answer is no. You wouldn't want to integrate it dt because this would not be Lorentz invariant. dt is not Lorentz invariant. What is Lorentz invariant is d tau. Another way of saying the whole same thing is we could include in the action just the integral of a mu dx mu. What does this mean? This means we go along the trajectory, we chop up the trajectory, and for each little interval, we take its dx mu, and we multiply it by a mu. A mu at that point, a mu right at that point, and we add them up. That's a quantity which is relativistically invariant. Why? Because it's the summation of a bunch of scalars, a mu dx mu, a 4-vector with a lower index times a 4-vector with an upper index. That's invariant. That's a scalar. And so we add them all up, we get a scalar. This is a good quantity to begin with. Now, I'm going to throw in one more factor here. I'm going to throw in the electric charge. That's just a numerical multiple, the electric charge of the particle. That ought to go in there. Why should it go in there? Well, if the electric charge was 0, then we should have no interaction with the electromagnetic field. So presumably, the strength of interaction between the electric and magnetic fields on the one hand and the particle is through its electric charge. So that's a reasonable thing to put in there. But this doesn't look like a conventional Lagrangian. Where's the velocity? Where's the dt? Where's the Lagrangian dt? Well, that's easy to fix. Just divide by dt and multiply by dt. What does this mean? It's integral e. Now let's take the time component. The time component would be a naught, naught for time, times, now what's x naught? X naught is t. So that's just dt by dt. That's 1. And then plus electric charge. Let's take the x component, a sub x times the x dt. What is the x dt? That's v sub x, right? That's the x component of the velocity. If we combine all of the terms, we'll just get a dot v dt. So somebody earlier said that the Lagrangian for, somebody earlier said that the interaction between the vector potential and the charged particle was through a dot v. Well, yes, that's right. You see it, but there's another term, integral a naught. This is the interaction. This is the Lagrangian. Or here, this is the action for a particle in an electromagnetic field. It's very simple. It's just a line integral of a dot dx.
Do we have an e squared there?
E squared?
Yeah, you have an e outside the parenthesis.
Oh, sorry. No e squared.
No one had seconded.
That's right. Yeah. E times a dot v. All right, I don't want to pursue this too much now, other than to make one observation about it. Just one observation about it, and that's that it's gauge invariant, that it has a certain gauge invariance, that is an action principle, thought of as an action principle, it has a gauge invariance. Yeah, even before I do that, let me relate some of this stuff to what's over here. Supposing I have a particle moving along a trajectory like that, and it's a charged particle. There's an electric current that flows. Both time component, there's an electric charge density, and there's a flow of charge. The flow of charge is just because the charge is moving. Now, where is the current localized? It's localized wherever the particle is. It's right sitting on top of the particle. So wherever the particle is, there's a flow of current if the particle is moving, and there's a charge density. The charge density is just describing the charge density of that single particle. So there's a flow, so there's a current along the trajectory of the particle. The space component of the current, the flux of the charge, that's proportional to the velocity of the charge. If the particle is not moving, there's no flow of charge. There may be a charge density, but there's no flow of charge. If the particle is moving, there's a flow of charge. So along this trajectory, there is a J. The time component is just the fact that there's a charge there, a charge density at the point where the particle is. And the space components of J, what are they proportional to? They're proportional to the electric charge of the particle times its velocity. It's right at the point where the particle is. There's a current which is proportional to the velocity, in the direction of the velocity, and of course it also involves the electric charge. Well, let's see, where did we have it? We had the Lagrangian, here it is, A dot V. What is A dot V? A dot V is clearly similar to, or E A dot V. E times V is the current. Where did I do? I lost it. Yeah, here it is. J is E times V. E times V is the current. This is the current dotted into the vector potential. Well, that's pretty much what you have over here. Current times vector potential. So we see there's a similarity. The similarity being that in both cases, the vector potential is coupled directly to the charge flow, to the flux of charge or to the density of charge. And I just wanted to point out that similarity at this point, that in both cases, it's charge current or current of charge times vector potential, which goes into the Lagrangian. The last thing I want to do is just talk about the gauge invariance of this Lagrangian. Is it gauge invariant? Not quite, but almost, and it's good enough. Let's look at the action between 2 points. What will it mean to say that the action is gauge invariant? Well, supposing the action changes when I do a gauge transformation, but it changes in a way that has no effect whatever on the motion of a particle. In other words, it changes in a way that, that has no implication whatever for how the particle moves. That's good enough to say that there's a symmetry. So let's see what happens. Supposing I make a gauge transformation on A mu. What does that do? What does it add to A mu? A mu goes to A mu plus 1 over E d mu theta, where theta is just this arbitrary function, theta of x. Any function, whatever, I can make such a gauge transformation. What happens to the action? The action gets an extra piece to it. We have to add to it E times the integral of the change in A, that's 1 over E, that cancels the E, d mu theta, that's the shift in A, times dx mu dt, d tau. Well, just dx mu, just dx mu. Anybody know what this integral is? From the starting point to the end point, along the trajectory, the derivative of theta times dx mu. The muth derivative of theta times dx mu.
The difference?
Yeah. And it's just the difference of theta between the endpoints of the integrand, between the endpoints of the integral. This is the change. Let's break it up into little pieces. This is the change in theta when you change x by a little bit times the change in x. Each little interval along here, this integrand is just the change in theta from going from one point to the next. When you add them all up, it just gives you the total change in theta in going from the initial point, theta initial, to theta final. Sorry, theta initial, theta final. This whole integral is just theta final minus theta initial. Well, why doesn't such a term in the action have any implication for the trajectory? Because it doesn't depend on the trajectory. It just depends on the value of the theta at the two endpoints, and it doesn't depend on the trajectory. No matter what trajectory you select, this integral here is always the same. It's just the difference of theta at the beginning and end of the trajectory. So, if this contributes something which doesn't depend on the trajectory, it will not have any influence whatever on what trajectory the particle takes. And in that sense, this is not an interesting contribution to the action. It has no implication for the motion of the particle. The important part of the action doesn't change. The part which really influences the particle does not change when you make a gauge transformation. So we see from this particle perspective that gauge transformations are also important invariances of the action of a charged particle with the electromagnetic field. So this time, we're not talking about a field carrying the charge. We're just talking about a point charge moving through space. So we see from two different perspectives that gauge symmetry is a fundamental symmetry of the interaction of charges with the electromagnetic field. Okay. I will be gone next week. I have to give a lecture someplace, a couple of places. And I'll be back the week after. How many lessons have we had so far? 7. 8? Seems to me it must be 8. Yeah. So we have 2 more. And I think we're getting somewheres. We've, but what I do want to go through now is the electromagnetic field, the equations of motion for the electromagnetic field, why F mu nu is connected to E and B, and to see that the electromagnetic field actually has the effects on a charged particle that you would expect. Namely, that it exerts forces of the electrical and magnetic kind. Then we could maybe spend a little bit of time with this and see that the flow of charge in this picture here also behaves as you would expect for charges flowing through space if the charges were described by this field. Okay, I think we're finished for tonight.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.